It's it's a great honor and pleasure that I present Yvette KOSMANN-SCHWARZBACH, honorary professor at École Polytechnique, formerly professor at Brooklyn College and the University of Lille. She did her doctor thesis on Lie derivative of spinors under the supervision of Andrei Liknerovich, and she has wrote many papers about differential geometry, algebra, and mathematical physics. The KOSMANN lift in differential geometry was named after her. The title of our presentation is Structure of Poisson Geometry, Old and New. You have the floor, please.
Thank you very much. J'essaierai de parler dans la langue de Shakespeare, étant donné que c'est la règle ici. Donc, je vais vous parler de Structures of Poisson Geometry, Old and New. It seems that every nook and corner of differential geometry is an important ingredient in the vast field of a geometric science of information. You have heard the words Riemannian, symplectic, Lie group many times, and they figure in the program of this meeting. It may be that Poisson is not yet in your vocabulary. I shall try to remedy this lacuna in my introduction today, where I will present the main structures of Poisson geometry and also some historical facts. That's the old part. And I will point out a few current applications. That's the new part, as the organizers of this conference have invited me to do. Can you hear me now? So this is what I intend to deal with in the present talk. What is Poisson geometry, and who was Poisson? This being said, I shall try and describe what are Poisson groups, what are Lie groupoids, what are Poisson groupoids, and also what is the infinitesimal of such structures, and also, at the end, I shall say a few words about courant algebroids, and I shall ask, what is the role of Dirac structures in the geometric science of information? Moi, je ne peux pas lire, c'est trop loin de mes yeux. OK, it will do.
Je vais avancer les slides si vous me passez le...
J'arrive à avancer les slides.
Ah non, je vais le faire. Non, je vais le faire. Je vais le faire. J'ai oublié, oui. Enfin, j'ai oublié. Oh, je suis à la suivante. Non. OK. So the question is, what is Poisson geometry? Well, it is a vast generalization of a geometric framework of Hamiltonian mechanics. It is the geometry of those manifolds where real valued functions can be paired by a bracket operation satisfying the properties of the Poisson bracket of functions on Cartesian space. And locally, defining a Poisson structure on a manifold, that amounts to defining the brackets of pairs of local coordinates. In addition to Poisson structures on finite dimensional manifolds, there is a large literature on Poisson structures on infinite dimensional manifolds. These are usually called Hamiltonian structures, and in particular, they're ubiquitous in the theory of integrable systems. But in this talk, I shall only deal with finite dimensional manifolds. So here is a portrait of Siméon Denis Poisson, who was born in 1781 and died in 1840 after a very full life of mathematical and physical publications. He was 17 years old in 1798, as you can compute, when he placed first on the entrance examination for the École Polytechnique, which the revolution had created 4 years earlier. And that's when he attended, among others, the lectures of Lagrange. So the story of Poisson geometry really begins in celestial mechanics. Lagrange, in his essays of 1808 and 1809, where he was dealing with the variation of a principal axis of the orbits of planets and on a general theory of the variation of arbitrary constraints in mechanics, had derived an expression by an involved procedure which in modern term can be explained as the inversion of a matrix of components of a canonical symplectic two form. And it was in 1809 that Poisson brackets as such appeared in Poisson's mémoire sur la variation des constantes arbitraires dans les questions de mécanique. This memoir was published in the Journal de l'École Polytechnique. I shall say a few words about Poisson, the mathematician, and also I describe him as an enseignant-chercheur because he was both a teacher and a scholar, and he had a dominant role in the science of his age, as well as in the administration of public education in France at all levels. So here on the slide, you have a few landmarks in his career. His first publication was in 1801. He was soon named assistant professor at the École Polytechnique, where he had been studying just a couple of years before. And then in 1809, he became a professor. Where did he become a professor? Well, at the Faculty of Sciences of the newly created Université de Paris. In other words, in Sorbonne Université. So we're continuing Poisson's teaching of 1809 and after. Then he became an academician, and if you try and compute the number of his publications, you will come up to nearly 200. No, that's not what I wanted to do. Yes? Poisson structures, we come to the subject of my talk. What is a Poisson structure? So we consider a manifold, call it M, and it will be called a Poisson manifold if a space of smooth functions over that manifold is a Poisson algebra. That is, there exists a skew-symmetric bilinear over the reals bracket, which is usually denoted by braces, on the space of functions, which one is a derivation in each argument, and two satisfies the Jacobi identity. And the Jacobi identity is written on the slide. The modern formulation that will extend to more general structures of Poisson structures is in terms of a bivector. What is a bivector in the lingua of the geometers? It is a skew-symmetric contravariant tensor of order 2, whereas a bivector field is, of course, a field of bivectors. So you can think of a bivector field as an object on which you evaluate a pair of differential one-forms in order to obtain a scalar function. Now, given a bracket, as in the definition of Poisson structures, you can define a bivector field, which I denote by capital P, P as Poisson, by the following formula. You define that the bivector P evaluated on the pair of differential one-forms df1, df2, that is by definition the Poisson bracket of f1 and f2. So in local coordinates, you have a formula at the bottom of the slide. If you denote the components of a bivector by P upper ij, the Poisson bracket of two functions f1 and f2 will be equal to the summation, which is written here. You consider the components of a Poisson bivector, and they're multiplied by the partial derivatives of the functions in the Poisson bracket. Now, I said the Poisson bracket of functions, by definition, has to satisfy the Jacobi identity. So the question is, if we use somehow the bivector P in order to define that Poisson structure, we have to know how to express the Jacobi identity. And the formula which is framed is the local coordinate expression for the Jacobi identity in terms of the coordinates of a bivector field P. So this being said, there is another remark which is important for geometers, that there is an invariant notion that corresponds to such a local expression. And that expression is called the Schouten-Nijenhuis torsion of a bivector P. And that is a trivector this time, which is usually denoted by P bracket P. And it is a fact that if you define the Schouten-Nijenhuis torsion as is usually done, then the local expression for the vanishing of P bracket P in the sense of a Schouten-Nijenhuis bracket is the formula in the frame. So you did not have a... That's correct, sorry. I forgot. So here is the Jacobi identity in local coordinates. And then my speech after that was to tell you that the expression on the left-hand side, this is just the coordinates ijk of the Schouten-Nijenhuis torsion of P. And now, because I said this is equivalent to the Jacobi identity, I can state the following theorem. A Poisson structure on a manifold is defined by a bivector field whose Schouten-Arrhenius torsion vanishes. One word in history. This identity is actually due to Jacobi. This is not always the time. This identity is named after Jacobi. And why is it named after Jacobi? Because he wrote it. When did he write it? We think it's about 1840, but it was only published after his death in 1862. And clearly Jacobi considered this identity to be a very important result. He wrote at the end of a statement of his theorem, quod est gravissimum theorema. So we are warned, this is important. I want to speak about Poisson geometry. It was Sophus Lee who essentially developed what is now known as Poisson geometry. When did he do it? Well, there's an 1888 paper among the numerous publications of Sophus Lee, where he introduced the components of a skew-symmetric, twice-contravariant tensor field and proved that the quadratic equation, which I wrote before, on these components and their partial derivatives is equivalent to the Jacobi identity for the associated bracket. Lee's work was partly forgotten, but it was rediscovered relatively recently, and there is a short paper by Alan Weinstein dating to 1983, where this is clearly explained. Now, you may be familiar with symplectic geometry much more than with Poisson geometry. So here is a kind of comparison between structure of Poisson geometry on the left-hand side and structure of pre-symplectic geometry on the right-hand side. So on the left, you have a bivector field whose Schouten-Arrhenius torsion tensor, torsion vanishes. And on the right, you have a differential two-form whose Durham differential vanishes. So I want to explain just a couple of other facts about symplectic on the one hand and Poisson on the other hand geometry. So given a differential two-form, it essentially amounts to a mapping from vector fields to one-forms. And I previously stated the definition of pre-symplectic structures, but now symplectic structures are those pre-symplectic structures such that this map from vectors to forms is one-to-one. That's the definition of symplectic geometry, really. And in the middle of the slide, which you can read, I wrote the local coordinates expression for the map omega flat. So why do I call this a musical map? Because it lowers the index of a vector field into a lower index of a differential form. Now, if you look at Poisson geometry, it's the mirror image of what I just said. There's a Poisson bivector field, which maps one forms to vector fields. And why is it also musical, and why is it denoted by P sharp? Because it transforms one form with a lower index into a vector with an upper index. Now, there is an important remark, if you're already familiar with symplectic geometry, is that there is a strong correlation between Poisson geometry and symplectic geometry, although both have rather distinct developments. But if a Poisson structure is non-degenerate, that is, if a map P sharp is 1-to-1, then in that case, you just have to invert that map, and what you obtain is a two-form, and is the map associated to a two-form, and that two-form turns out to be closed. So, in fact, invertible Poisson structures are the same as symplectic structures. And in a way, you can say that Poisson geometry generalizes symplectic geometry. As far as examples are concerned, I will be very brief. Of course, Cartesian space with standard coordinates, if it is even dimensional, carries a non-degenerate Poisson structure. That's the Poisson. These are the Poisson brackets of classical mechanics. Now there's another example, and that is the example of the dual vector space of any Lie algebra. So you consider a Lie algebra, it has structure, you consider a basis in that Lie algebra, and it has structure constants, C, I, J, K in coordinates. Now, if you set P, I, J of Xi equals sum over K, no. Where am I? Okay. If you set Pij of Xi equals sum over K ofCijk Xk, what you obtain is a bivector on Xi star, and you'll excuse me, but the place of the indices is wrong with respect to what I explained before, but there is a reason. That's because we're dealing with a dual of a space, and the statement is that whenever theCijk are the structure constants of a Lie algebra, then this expression defines a Poisson structure on the linear space G upper star. And here is a very simple example in the standard coordinates of SL2R. So this is a lecture on Poisson. And so far, I have spoken about Poisson structures on manifolds. And from now on, I will mostly speak about Poisson structures on various kinds of manifolds. So the first kind of manifold that we'll have to examine is the case of Lie groups. And this goes back to work of Drinfeld in 1983, where he introduced Hamiltonian structures on Lie groups, Lie bialgebras, and he explained, that's the title of his article, the geometric meaning of the classical Young-Baxter equations. And he defined what he called Hamilton Lie groups. Now, when he spoke a few years later at the International Congress of Mathematicians in Berkeley, his lecture was where he defined the notion of quantum groups, but he introduced in his lecture the semi-classical limit of quantum groups, and that are Poisson-Lie groups. Now, they are most often called Poisson groups, and I will call them Poisson groups for short. So essentially, the theory of Poisson groups is the intersection of the theory of Poisson geometry with Lie theory. And when you look at both theories together, you somehow have to introduce some compatibility condition between the two theories. And what is the compatibility? It is called the multiplicativity of a bivector field. So you consider a Lie group, call it capital G, and a bivector field, capital P, on that group. So it's a field of tensors which are covariant of order 2. And you assume that this bivector field satisfies the equation which is written in the middle of the slide. And this is very easy to explain. You want to consider the value of P at a point which is the product G times H, where G and H are 2 points in your group. And you're going to assume that that value is the sum of 2 terms, the first of which is P evaluated at H, but left translated by G, and the second term is P evaluated at G and right translated by H. So this is the definition of a Poisson group. What is the infinitesimal of a Poisson group? The infinitesimal of a Lie group, of course, is a Lie algebra. In a Poisson group, you have an additional structure on the Lie algebra of a group. And that additional structure gives the Lie algebra the structure of what is called a Lie bi-algebra. That is, both G and its dual space have a Lie algebra structure. And then the infinitesimal form of a multiplicativity is going to give you a compatibility condition between these two infinitesimal structures. And that is explained on the slide. And maybe I should be brief on that. You need to consider both the bracket on G, the bracket on G star, and then you want to express this condition by looking at the transpose of the bracket on G, which is a map from G to wedge 2 of G. And the condition is that this map, transpose of gamma, be a Lie algebra cocycle of a Lie algebra G with values in wedge 2 of G with respect to the adjoint action defined by the Lie algebra structure mu on G. And there is a theorem that this notion of Lie bialgebra is actually self-dual. If G with mu and gamma is a Lie bialgebra, then G star with gamma and mu is also a Lie bialgebra. I spoke about Poisson group, and I told you the infinitesimal of a Poisson group is a Lie algebra, bialgebra. So this is the statement, the formal statement of what I announced a minute ago. And how do you see that this theorem is true? Well, you start from the Poisson group, and it has a bivector field defining the Poisson structure. Now, if you look at the value of a Poisson bivector at the identity, it turns out that it vanishes at the identity because of a defining formula. P at E is PE plus PE. So this shows that this map can be linearized, and what it yields is a linear map from the Lie algebra G to the exterior power wedge 2 of G. Now the transpose of this linear map will define the Lie algebra structure of G star. In other words, the Lie algebra structure of the dual of a Lie algebra, that's the linearization of a Poisson bivector. And where does the cocycle condition come from? Well, it's the infinitesimal of a multiplicativity condition relating P to the group structure of G, which is itself a cohomology condition. I shall take a sip of water before I tell you about groupoids. Maybe I should put the slide on. Okay. Alors, are we with groupoids already? Yes. So we hop from groups. We hop from groups to groupoids. So that's a big jump. The theory of Lie groupoids was developed from the beginning of the 20th century. No, not from the beginning, from the second half of the 20th century, by many people whose names are famous, I hope. And the continuous development of this theory is very notable with the work of many more younger people, and probably many more names which I should have noted here. I'll just read from the introduction of Mackenzie's book, which is one of the best references, probably the only reference, and a very good one, on Lie groupoids and Lie algebroids. In his book of 2005, he wrote, "A case could be made that the modern concept of Lie group has been a transitional stage in the evolution of a notion of Lie groupoid." In other words, you can certainly look at the theory of Lie groups as a particular case of this vast theory of Lie groupoids. So groupoids are objects which generalize groups, and in particular Lie groupoids generalize Lie groups. To give you just one example that may speak to you, what is the path groupoid of a topological space? Well, it's the space of maps. And how is multiplication defined there? Well, multiplication is defined by combining two paths if the target of one is equal to the source of a second. Now, there follows a brief and formal definition of Lie groupoids. So you consider two smooth manifolds, gamma and M. M is called the base of a groupoid, and gamma is the total space of a groupoid. And there are two maps. One denoted by alpha is called the source. The other one is denoted by beta. It's called the target. And they're assumed to be surjective submersions. Now, on gamma, there is a partially defined associative multiplication where G and H in gamma have a product G times H, which is defined if only if the source of G is the target of H. Think of successive maps that you can compose. And you assume this smoothness of a multiplication map, and in addition, you have the existence of inverses, of one inverse for each element. The space M is called the base of a groupoid, and it is identified with the units of a multiplication. To give a couple of examples, you have an example of a pair groupoid, and what I should have said to begin with that is any Lie group can be considered to be a groupoid over a point. And then here you have a definition of another class of important examples. These are the gauge groupoids, which are composed of pairs in the product of a principal bundle with itself, as explained on the slide. So we know that the infinitesimal of a Lie group is a Lie algebra. What is the infinitesimal of a Lie groupoid? Well, I'll give you a definition. What is a Lie algebroid? A Lie algebroid is a vector bundle over the reals. And you assume that you can pair sections of the vector bundle to obtain another section. Denote this by a bracket, as usual. And you assume the existence of a map from the vector bundle to the tangent bundle of a base. And all these elements of a structure are related by the condition in the frame, which says that you do not have linearity with respect to functions, but there is an additional term which is obtained by looking at the anchor, evaluating on the section X that you have in the equation. This gives you a tangent vector field, and you apply that to the function f to get a function, and you multiply the second entry y by that function. Now, what is the interest of this definition? Well, first of all, it vastly generalizes the notion of tangent bundle, because the tangent bundle itself verifies the axioms of a Lie algebroid in the sense that the anchor is just the identity map, and the equation in the frame is then satisfied. And a special case of Lie algebroids is the case of Lie algebras. And another very important example in differential geometry is that the cotangent bundle of a manifold is a Lie algebroid. And the defining property of that Lie algebroid is written here. df1, df2 bracket is the differential of a Poisson bracket f1, f2. Okay. So why does one speak, number one, of Lie groupoids and number two of Lie algebroids? Well, because each Lie groupoid has an infinitesimal, which is a Lie algebroid. And here is a short summary of what is the Lie algebroid of a given Lie groupoid? Well, it's not very hard to consider that. And here you have a definition of the bracket and the anchor in that case. So maybe I'll take a breath and ask, is there information geometry on Lie groupoids? That's a question for this audience. Well, I tried to look at the literature, and I did find two very recent papers by Grabowski, Kusch, and Marmot, where they argue that the proper geometrical setting for some problems in information geometry is the setting of Lie groupoids and Lie algebroids. So here you have, in the bottom, you have a reference to their papers, and I tried to follow what they are doing. They essentially explain that a contrast function gives rise to both a symmetric two-form and a symmetric three-form on the Lie algebroid of a Lie groupoid. And then they look at the particular case of a pair groupoid M cross M. In that case, the Lie algebroid is just the tangent bundle of M, and in that case, the contrast functions are differential forms of degree 2 and 3. So maybe some interest for information geometry is in those recent papers. Next topic was still dealing with Siméon Denis Poisson, but in very modernized form, the notion of Poisson groupoid. Of course, you have guessed already, Poisson groupoids, they generalize Poisson groups. But in what sense? Well, historically, it's interesting that the defining property of Poisson groupoids, which is, of course, the compatibility between a Poisson, between a Lie group structure on a manifold and a Poisson structure on that manifold, where this compatibility was defined initially, historically, in two different ways, by Alan Weinstein and by Kirill Mackenzie. And the equivalence of these two definitions was proved 2 years later by Mackenzie and Ping Su. What did Weinstein do? What did he write? Well, he first needed the definition of what's a coisotropic submanifold of a Poisson manifold. And that's easy to state. You just assume that the Poisson bracket of two functions which vanish on the submanifold vanishes on the submanifold. And Weinstein observed certain properties of the Poisson structure of a Lie group when it happens to be a Poisson group, various equivalent definition of these structures, of this structure, and one of those could be transposed, generalized to the case of groupoids, and that's his definition of Poisson groupoids, which is stated here. And what did Mackenzie do? Well, he observed other properties which are not completely obvious. One is that the tangent bundle of a Lie groupoid is a Lie groupoid over the tangent of a base, whereas Yes, it's easy to read, but not for you. The cotangent bundle of a Lie groupoid is also a Lie groupoid, but this time over the dual of a Lie algebroid of gamma. Then this being said and proved, then Mackenzie could define a Poisson bivector on a Lie group G to define a Poisson groupoid structure on G if a map P sharp from the cotangent to the tangent bundle, in fact, groupoid in this case, is a morphism of groupoids if it preserves the multiplicative structure of a groupoid. And then the equivalence was proved 2 years later. Again, one has to ask, what is the infinitesimal of a Poisson groupoid? And the answer is it's Lie bialgebroid. And you have to give a definition and to prove that this is indeed the infinitesimal of a Lie groupoid. So again, you have a pair of Lie algebroids on vector spaces which are in duality, and there is a compatibility condition between the Lie algebroid structures on A and on A star. And this is explained here because from the Lie algebroid structure of A, you can construct by the generalization of a Dirac differential, A differential on the sections of the dual, whereas you have the original Lie algebroid structure of A star, and the condition that you impose is that this differential be actual, which is defined in terms of the structure of A, but now acts on A star. This should be a derivation of a Lie algebroid bracket of A star. And again, there is a result which is not completely obvious, that if A star is a Lie bialgebroid in the sense I just described, then A star A is also a Lie bialgebroid. That is, the notion of Lie bialgebroid is self-dual. Well, we're leaving Poisson and coming to Dirac. Drinfeld, in his 1983 paper, actually defined the double of a Lie algebra. And that's fairly straightforward now statement. And the question arose when Lie algebroids were being studied in differential geometry, whether this condition, this construction, or this theorem of Drinfeld could be extended, generalized to the case, to the oid case, replacing a Lie algebra by a Lie algebroid, or a Lie bialgebra by a Lie bialgebroid, a notion which I just described. Now, Dirac geometry, what we now call Dirac geometry, is the geometry of the doubles of Lie algebroids. That is, you take a Lie algebroid A, you take its dual A star, and you take A plus A star, direct sum of vector bundles. Now, there's a concept of Dirac structure which originated in Dirac's theory of constraints, and that concept unifies the geometry of two forms with the geometry of bivectors on manifolds. Therefore, they're unified two types of structures which I described briefly before. That is the pre-symplectic geometry and the Poisson geometry. Two forms on the one hand, and bivectors on the other hand. What is new, at least to me, is the appearance of Dirac geometry in information geometry. And I shall try and say a few words about that. How much time do I have? How much time do I have? 5 minutes. Okay, I might be able to make it. Okay. So, to describe this passage from GG star to G plus G star, or A star to A plus A star, we consider a simple, rather simple case where the Lie algebroid A is just the tangent bundle of a manifold, Tm. And in that case, we can look at the direct sum of the vector bundles Tm plus T star m, which is denoted by capital Tm, and which is called, in the literature on information theory, it's definitely called the Pontryagin bundle, whereas in the literature of differential geometry, you will find many other names, in particular generalized tangent bundle, or big tangent bundle, or the double of the tangent bundle. So let's consider the Pontryagin bundle. Can one define a bracket on the Pontryagin bundle of a manifold M? So this problem goes back to the 1990s, when a student of Alan Weinstein submitted his thesis and wrote an article explaining that, yes, he could define a bracket on T plus T star M, extending, of course, the Lie bracket of sections of T, and this bracket had the good property of being skew-symmetric and the bad property of not satisfying the Jacobi identity. Then he defined vector sum bundles of Tm plus T star M, which he called Dirac structures on M. Later, the courant bracket was proved to be the skew symmetrization of a bracket, with the important property of satisfying the Jacobi identity in a form suited to the non-skew symmetric case. So what is the bracket in the Pontryagin bundle, which has the good property of satisfying the Jacobi identity? It's written in the middle of a page. And the bad property, if you like, that it is not skew symmetric. And you have a formula here, and if you look at the particular cases which are written in the middle of a page, where you take one vector field and one form, so this gives you one form, which is the Lie derivative of a one form with respect to the vector field, whereas if you take that same one form and that same vector field, but in the opposite order, you obtain a completely different result, the interior product of a differential of a one form with respect to the vector field. But this non-skew symmetric bracket satisfies the Jacobi identity in the form which expresses the fact that taking bracket with an element U of a bracket VW is a derivation. Bracket U of bracket VW, that's bracket of UV bracketed with W plus V bracketed with UW. So this bracket is called the Dolphin Bracket. It was introduced in, not in the context of differential geometry, but in the context of study of, again, integrable systems by Irene Dorfman in 1993. And if you're interested, you could look at my paper, which is on archive, about courant algebroids. So what is a Dirac structure in a Pontryagin bundle? Well, it's a subbundle of Tm plus T star m, which is maximally isotropic with respect to the canonical fiber-wise bilinear symmetric form. And if you have a Dirac bundle on a manifold M, you will say that M has a Dirac structure. Now, there is another situation, rather a special case of that situation is when you assume that the sections of that subbundle defining the Dirac structure form a closed subalgebra, Lie subalgebra, under the Dolphin bracket. And in that case, you will speak of an integrable Dirac bundle. And again, be careful, in the math literature, the term Dirac bundle is usually reserved for those Dirac bundles that are integrable in the sense of this definition, of this second definition. What is the interest of introducing Dirac structures? Well, they are very interesting from the conceptual, very interesting notions from the conceptual point of view, because they unify contravariant and covariant, if you like. The graph of a bivector field is a Dirac structure, whereas the graph of a differential two-form is also a Dirac structure. So this is a common generalization of, say, Poisson geometry and symplectic geometry, or pre-symplectic geometry. So to end my long discourse, I will just point out that Pontryagin bundles occur in information geometry, in information theory, and I will point out the work of François-Gay Balmaz and Hiroaki Yoshimura, which you are probably familiar with, which was in particular published in the lecture notes of 2017 and 2019. So I will not have time to describe the little I understood of those theories, but this is really the connection in the non-technical sense of everything I tried to explain today and information theory, information geometry. Now, there is much more on Poisson geometry than I was able to explain. There are more notions such as the doubles of Lie algebroids, the notion of Dirac groupoids, etc. And also on the, to come back to Siméon Denis Poisson, what he introduced, what he introduced in 1809 gave rise to Poisson geometry as I described it, which itself gave rise to quasi-Poisson geometry and G, quasi-Poisson and such structures, as well as all the structures up to homotopy, which are very important now and developing at a fast rate. Are there more applications of the diverse theories that evolved from the early work of Siméon Denis Poisson and Sophus Lie to the science of information? Maybe someone in this amphitheater or someone who is listening from afar will say, yes, I have important implications of some aspects of the structures of Poisson geometry to the geometric science of information. This is how I will end my talk, and I will wait for your questions.
Thank you very much. Yes. There is possibility of question also for persons online. But first question in the room. Could you go here because the sound is better?
I'll need an interpreter.
Thank you.
Thank you very much. I would like to know your opinion on the curvature in the Poisson manifold, because the concept of curvature in the general relativity is the gravitational force. In the Young-Mills theory, the concept of curvature is the interaction between the particles, fundamental interaction, and the concept of the curvature in the Hilbert space in quantum mechanics is the quantum force, such as Casimir effect. Now, I would like to know your opinion on the curvature connection and curvature on the Poisson manifold, which is in infinite dimensional manifold. Thank you very much.
Yes, it's not very easy to answer your question because curvature is usually defined in terms of Riemannian structures, not in terms of Poisson structures. So I assume you can combine the two approaches and have both a Riemannian structure and a Poisson structure. But in fact, the curvature, the natural notion of curvature in the case of bivectors is this vanishing or non-vanishing of the Schouten-Einhaus bracket, which is a tensor, contravariant tensor of order 3, which somehow measures it measures the lack of Jacobi identity, the lack of integrability in a sense. But right now, maybe if I look at more papers or if I think more slowly, I can think of references that would maybe connect the two approaches.
Thank you very much. Merci.
Yeah, I meant to show a few references while we have questions, but I don't know whether you see them. Yeah.
Yes, Yvette. There are theorems. There are theorems which show that
yes.
Poisson structures can be reconstructed from symplectic leaves and transversal Lie algebra structure. And for the other structure you show, for example, Poisson groupoids or Dirac structure, does this kind of theorem of reconstruction exist?
I'm not sure I'm not sure the reconstruction exists, but the foliation will exist. There will be symplectic foliations associated to Poisson bivectors on Lie groupoids. Now, who has worked on that? I don't think you have a foliation by symplectic groupoids. No, but something exists. I'm pretty sure, but not as straightforward as symplectic leaves in a Poisson manifold.
Thank you. in fact, if there is no other question, I had another question, because the multiplicativity of P, in the case of Poisson group, as you say, is a cohomological nature for a module to the right and to the left for the group. And do there exist also that for the groupoid?
Yes, that's fairly well known, I think. Yeah. No, the extension to the Lie groupoid situation has been studied, and the cohomology of groupoids is quite a big field of investigation, and the case of Poisson groupoids, of course, will give some interesting results that will connect the Rime type with Poisson cohomology type results. Yeah. Okay, two questions that have to be answered at length, I think. Yeah, thank you.
So, thank you very much.
Oh, I have the brochures of the Poisson book, and even of the Poisson exhibit that took place at Jussieu a few years ago. But these are actually ads for the book on Poisson, which I edited a long time ago. So they can be picked up if you like.